The talk is all about like navigating EVM chain security, that is like smart contract vulnerabilities. Uh, just exploring like what are the common attack vectors on smart contracts which are deployed on EVM chains. So about me, I'm a web and smart contract triager at Immunify. So Immunify is a leading bug bounty platform where we connect with hackers, with projects, and we work as a mediator between like validating what are the valid submissions from white hat and then escalating that submissions to the projects. So I like to create like educational content on security as well, like highlighting some of the DeFi hacks, also like writing bug fix reviews, like what are the submissions that got paid through Immunify, and also interested in investigating like EVM based DeFi hacks. So previously, like before exploring the Web3 security space, I also worked as an AppSec engineer in Web2 space. So this is like Immunify Medium, where all the bug fix reviews and all the articles related to vulnerability gets posted, and also we have a community challenges where all the vulnerability patterns related to smart contracts gets published, so people can enjoy the challenge and can upskill their smart contract hacking skills. So the agenda of the talk is we will be exploring like what are the top 5 common smart contract vulnerability patterns that developers often do, leading to like different types of attacks. So we will be exploring specifically to EVM chains, that is mostly written in Solidity or Viper. So we will explore each such vulnerability case by the description, by some of the examples, and how we can prevent those attacks. So these are the 5 common patterns which is listed here, which is like improper input validation. Like developers often miss validating the user input, whatever the user inputting into the contracts, and what are the outcomes of uh, such missing checks. Then the second is like incorrect calculations, where developers like doing like a very inconsistent with calculations logics, leading to like unexpected behavior in the contracts. And the third one is like many of these contracts has some kind of dependencies, like some depend on Oracle, some depends on Dexes to get some data, but they do it in a very insecure fashion, like leading to like some of the attack vectors, like Oracle manipulation is a popular one. And the fourth one is like front running, which is a classic feature, which leads to like sandwich attacks. So we will explore all these cases, and the last one is like insecure external call. So all the contracts communicates with each other, and they make like external calls, and what could go wrong, like when you can't able to handle like how you should like safely call an external contract, and how it can lead to like attacks like reentrancy. So the first one is like improper input validation. So validation are crucial for all the applications and all the contracts, because the application and a function should be aware like what kind of data it's expecting from the user input. So failing to do that, it can lead to like unexpected behaviors in the contract. It can lead to like injection of malicious data. It could abuse the contract logic, and it can lead to like many other behaviors. So we're going to explore some of these cases by some examples. So here's the case one, which was taken from Zapper Finance postmortem bug fix review. So you can see there is a Zappot with permit function, which is basically responsible to just zap out your funds. And you can see it takes the parameters, that is like from pool address and as well as like permit data. So the whole issue all around is like you can see the highlighted line, which is like it's taking the user input from pool address, and it's making directly call with user pass permit data. So permit data is basically like you're giving allowance, like an approval with a signatures, right? It should be giving approval, but user can like arbitrarily inject any kind of arbitrary data here. perform any unauthorized action because there is no validation going on. There is no sanitization on this permit data parameter. So what attacker can do, he can ABI encode the transfer from functionality of ERC20. And what happens when he pass it with a LP token? So all the tokens from victims get transferred to the hacker address. So this was the simple, straightforward attack, and there is a bug fix review article also written on Immunify, and it was reported through Immunify, and the hacker got paid. And the case two is for Sovian, which is a borrow lending platform on RSK blockchain. So they have this function called borrow, and you can see it has multiple parameters, and the specific parameter to notice is the loan ID. So what happens over here is the functionality over here is user can provide the loan ID, and the function verifies if the loan has if the user has like unused collateral. So in order to borrow loans on a DeFi protocol, you must first supply collateral, then you can borrow based on collateral ratio. So what happens over here? They are not even validating like if the loan ID actually belongs to the caller. So what happening over here? There is an access control check missing. So any malicious user can input the loan ID of another user, and he can directly take a loan behalf of any other user. So it was a simple, straightforward bug where there is access control missing, and there is also it was reported through Bug Bounty platform and was got paid. And there is a bug fix review in the article below. And the next common type of attack pattern, like a vulnerability pattern which developers do, it's like they use they often have incorrect calculations. Like smart contracts have this calculation logics, and it's not very inconsistent. So what attacker can do, attacker directly attacks the logic of the contract. So instead of finding traditional bugs like reentrancy, underflows and all, so attacker directly try to attack the logic of the contract, try to find the inconsistency in the calculation. Like this can be due to flawed math operations, like if the contract is doing some addition, subtraction, division or multiplication, you can find some issues around. Or it can be due to incorrect decimal handling, because in ERC2, ERC20 tokens, different tokens have these different decimals. Like usually there is no standard around. People follow 18 decimals, but if you take USDT or USDC, it has 6 decimals. And fail to properly validate those decimal handling, leading to unexpected behaviors in the contract. And also it can lead to some of the cases where let's say you just deposited some of your funds in the lending platform where it generates yield, and a hacker found a way to manipulate some calculations where it is leading losses to all the other users. Like it's not giving them the exact yield. So he found a way where he can use the max operation to manipulate that yield generation. Also incorrect share allocation on the pool. So whenever you deposit into the pool, you get shares allocated to that pool. So in this way, he can manipulate and he can get max shares out of the pool and can dump that LP shares later and can get his deposited tokens more. And there are many more attack vectors which can be done. So one of the simple example is we will take this example which has a function which says swap DAI for USDC, and what it does is basically function that takes your DAI tokens and swap it back with USDC tokens. And there is a statement there is a variable which says DAI to take, and what it does, it takes whatever the user input amount of USDC import and it doing the conversion. The reason why it's doing the conversion with 1 to the power of 12, it's DAI is 18 decimals and the USDC token is 6 decimals. So the issue over here is user can, malicious user can make the DAI to take variable to 0. And how he can do, he can just basically supply a small amount of USDC, and when it is divisible by 1 to the power of 12, it gets rounded to 0 due to the rounding issue here. So basically, attacker can swap without giving out any of the DAI tokens, and he can get back all the USDC tokens from the contract. So again, it is due to the incorrect handling of decimals, due to the various tokens having multiple decimals, different types of decimals. So what are the preventions of like input validations and incorrect calculations? Like for the validating the user inputs, like always make sure to whitelist what to exactly receive from the user input, and do not allow like other things which is not required. And also like if it is the integer value, try to have like bond ranges, making sure the value is within the bonds, and also like properly validating the formats. But usually what most of the projects just rely on unit testing. So what I think is unit testing is not sufficient, because in unit testing, we only write the test, just making sure that functionality works in an expected behavior. So we are already aware like what is going to be the output of that functionality and all. So unit testing is not enough. So we should always do fuzzing around all the functionality, because fuzzing is really helpful, like highlighting what could go wrong. Like it can show us like smart contract functionality can behave in unexpected ways. Like it can highlight that gray zone which is missing with unit testing. And as well as like instead of like rewriting all the libraries for performing operations, for example, like arithmetic operations, like you can use well-tested and well-established libraries. Like from OpenZeppelin, there is a SafeMax library, so you can also rely on such libraries. Coming to the third type of attacks, vulnerability patterns is like insecure external dependency. As we know that smart contracts has some kind of dependency on each other. Like it could be Oracle dependency, where they wanted to call to some kind of Oracle, wanted to extract what's the price of the token, or they wanted to call to some DEXs, just wanted to get like what are the reserve ratio, what is the liquidity of some kind of token over there. But like there is a like the issue with this dependency is like if the developers are not really aware, like if something happens to the dependency, like let's say hacker exploits the vulnerability in the dependency itself, and how could it impact our application? The developer must be aware, and like he should always think like what could go wrong in that situation, and should always have that plan B to handle such situations. So we will explore one example of insecure external dependency, that is like price oracle manipulation. So first, let's understand like what is price oracles. They are basically the tool or contract who is to give the price of an asset. Like if you wanted to understand, if you wanted to know that what is the price of like Ethereum, you can use Oracle to know what is the price of given asset. So there are two types of oracles as like which are popularly which are off chains and the on chains. So we will be focusing on on chain oracles, which are mostly rely on the topmost which are Uniswap or Balancer, which uses like AMM product to determine the price. And the price is determined based on the ratio of tokens present within the pool. So we will explore like how on-chain spot price calculation happens. So let's say if you wanted to determine what is the price of Wrap BTC, like if you wanted to buy one Wrap BTC, how much Ethereum token you need to pay. So what on-chain spot price works like, it goes to the Uniswap pair of Ethereum and Wrap BTC. It grabs the reserve balance of both the tokens, like Ethereum and the Wrap BTC. Then it's like Y by X. Let's say the pool has like 20 Wrap BTC and the pool has like 100 Ethereum. So in order to understand the price of like Wrap BTC, it divides like 100 by 20. So we get like it's 5 Ethereum. So basically it means like you need to pay 5 Ethereum to buy one Wrap BTC. So you can easily see how the price is calculated based on the reserve ratio, and how it is easy for hackers to like manipulate the price just by swapping each other tokens. So it moves the price. So what hackers do, they use flash loans. So protocols who are using on-chain spot price, they use flash loan vulnerabilities. They take loans, they make large swap, so that they can manipulate the pool of the oracle to return some highly inflated price, and they exploit like platforms who are relying on on-chain spot price. So we will understand this scenario, how on-chain spot price is exploited by the hacker on a like borrowing lending platform as an example. So here's the diagram. Let's say there is a user and there is a vault. Vault is basically a smart contract. Let's say it's a borrowing lending platform contract, and it's relying on Oracle, Uniswap Oracle. So the user has like one Ethereum, and user wanted to like supply one Ethereum to the vault because he wanted to generate some, like he wanted to borrow USDT in return. So he wanted to supply one Ethereum as a collateral. So what Vault does? So what contract does? It wanted to determine like how many USDT tokens I need to give back to the user. And the way it determines, it makes a call to the Oracle asking like, hey, what's the price of one Ethereum? Like how many USDT tokens I can issue back to the user. So it tried to query the price of one Ethereum to the Uniswap, and the Uniswap returns like it's $1,000. So what Vault does, it gives like under collateral loan, which is like 900 USDT to the user. So this is the normal workflow of how borrowing lending platform works. Now let's look what attacker can do, because you can see when the Vault query the price of one Ethereum, it try to return what is the last price it has based on the reserve. So what hacker can do? Hacker has like 10,000 USDT. He can directly go to the Uniswap pair. He can make a large swap buying Ethereum, and buying that Ethereum, like it inflates the price, increase the price of that Ethereum. So now, once the price is inflated, he can take the 8 Ethereum and he can supply that 8 Ethereum to the vault, that is the borrowing lending platform. And now the vault again make a query to the Oracle asking, hey, what's the price of one Ethereum? And the vault returns like it's 10,000 per Ethereum. So the attacker has like $80,000. So the vault said that you can borrow like 72,000 of USDT tokens in return. So this is how he first manipulates the Oracle, then he exploits the vaults which is relying on on-chain spot price. So what are the solutions to this? This is like a very complex problem. Like many contracts have to rely on oracles to understand, to determine what is the price of an asset. But so there are two popular solutions which projects have been doing. The first one is the top, relying on the top, which is like time weighted average price. Like instead of like relying on the last traded price, they are trying to take average price between the different time intervals. But again, it's not a bulletproof. Like we have seen in the past, like even projects relying on the top Oracle mechanism, they also gets hacked in case of like projects having less liquidity. And the second mechanism is like instead of relying just on one Oracle, they rely on like multiple oracles, and they take like a median price across all the oracles. The fourth type of common attack vectors is like front running. So developers often make themselves vulnerable by writing code in a such a way where they are vulnerable to such manipulation, where someone can take advantage and can influence the outcomes of something. Like it could be exchange, auction, or it could be like a simple swap. So basically front running is like basically an act of reordering the transaction, where he puts the attack transaction in front of a pending transaction so that he can manipulate the outcomes first, so that the user gets a bad price or something. And the common case with the front running is like again with the swapping. So multiple projects have this swapping feature where they wanted to swap one token to another, and the way they do, they integrate these routers, Sushi or Uniswap routers, and they swap the tokens. But the problem with with those is like most of these protocols have hard-coded minimum amount received. If you see zero, which basically like saying like uh, the project is agreed to receive like 0 tokens in return, like in case something goes wrong. So it's basically like a slippage. If you know what is slippage, where we set a slippage from a front end. So in that case, it's setting slippage to the 0. So what could go wrong? So what attacker can do, he can basically sandwich the transaction where he can spot that swap contract is making the swap where he has like slippage set to 0. He can go and he can basically manipulate in such a way where the contract receives very less amount of tokens in return, or maybe 0, because it has this condition where it accepts that. And the fifth common type of vulnerability pattern is like insecure external calls, which is contracts basically do external calls. And we know the reentrancy vulnerability, which is a classic vulnerability the hackers use. So that is exploited by a call method of Solidity. So reentrancy vulnerability happens whenever the contracts makes an call to an external contract, which is like a untrusted contract, and that untrusted contract makes a recursive callback to the target contract to do something malicious, like to steal funds or do something which is profitable for the attacker. So let's understand with a simple example. So we have the function withdraw balance. What it does, so whoever call this withdraw balance, the amount to withdraw variable stores whatever the user balance has. Then it makes a call to the user, that is like transferring whatever the user balance it has. Then it's checking whether the call was success, the transfer was success, and then it's updating the states like, yes, transfer was successful, let's update the balance to 0. So what's the issue here? Let's suppose this is the exploit contract which has this fallback function. So whenever the funds are transferred, this fallback function will get triggered, and it's making a recursive callback to this function itself. So what's happening? Withdraw balance is call, user balance is retrieve, and again message sender call will trigger this exploit contract, and this exploit contract will again trigger this condition. So this will go in a loop until and unless it drains all the funds from the contract, so it does not hit the next condition. So how to fix this vulnerability? So there are two like prevention methods which are a popular one which developers use. The first one is like mutex locking. They have these modifiers where they have like non-reentrant where they just have variables which is set the condition to true, and you're not able to lock, you're not able to re-enter into that function until that condition is set to be false. So this is how the first popular one. And the second one is like just to follow like checks effects interaction pattern, where you're retrieving the balance first. Once you retrieve and store the balance in amount to withdraw variable, you are just updating the state next. So you're updating the balance to 0, and lastly you are doing it like an interaction part where you are interacting, that is like sending the balance to whoever like message or sender is, and you are checking. So even if he try to re-enters, his balance is already set to 0. So re-entry has no effect on this one. And the last one is like, there is one more popular method which is coming, which is still in draft, which is EIP 5283, which is addressing this issue at a EVM level, where they introduce like two transient storage, where the storage, where the like execution will be stored with a T load and a T store, where like whenever the transaction is executed, all the changes read and write will happen within the transaction. So it's an interesting EIP to look for to address this issue. And the last is I just collected some of the resources. So some of you like who wants to get started with like smart contract hacking, especially on a EVM chains, I just listed all the links, and like that's it. Like that's my Twitter handle in case you wanted to follow. And thank you.